So this is an introduction to waves. Waves, when it comes to the test, will be combined with harmonic motion and sound, and then we'll have a separate test over light when it comes test time. But waves here is kind of the introductory topic and it applies both to sound and light. So we're going to introduce a lot of terms here that will come up again and again and again as we cover light and sound. So these are just general properties of waves. So first off, just some terms to get out of the way. A wave is nothing more than a disturbance in space that transmits energy. And so the way I like to think of waves actually is the stadium wave, where the crowd's, jumping up and throwing their arms up in the air. The disturbance, the people throwing their arms up into the air, goes around the stadium maybe, but the people themselves don't move that much. They vibrate in place and that's it. That's exactly what a wave does. A wave transmits the energy. It disturbs the medium, the stuff that carries it, but the wave itself doesn't really move. Ocean waves do the same thing, except when they get close to the shore and start to break, then the physics gets complicated. But ocean waves, for the most part, the water bobs up and down, and it passes energy side to side, and that's all that happens. Is you get a little bit of up and down, maybe a little bit of side to side sloshing, but you don't end up with the waves out, the water out in the middle of the Pacific ending up on the California coast. Every time a wave comes in, you instead have that water just passing on the wave energy to the next chunk of water, to the next chunk of water, to the next chunk of water. The medium, as I've already mentioned, is the material through which the wave travels. And as I said, the medium doesn't travel with the disturbance, but instead vibrates in place. For ocean waves, the medium is water. For sound waves, the medium is air. For light waves, there actually is no medium, which is one of the interesting things about light waves, in addition to the fact that light can be both a wave and a particle. More on that another time. Anyway, period, which is abbreviated with the capital T, you've probably seen this term already, but period is how long it takes one wave to pass a given spot. It's measured in seconds, and it's really because it's a time measurement. Period is equal to time divided by number of vibrations, and so then that's your formula there. I don't have an abbreviated version of that formula typed up, I don't think. Frequency is kind of the inverse of it, and frequency is the number of vibrations in 1 second. And this is measured in 1 over a second, or hertz. We tend to use period for slow waves and frequency for fast waves. But anyway, the formula for frequency is the number of vibrations per second. Notice it's the exact opposite. Really, it should be vibrations per time, though the standard is to use seconds. Also, there's a picture of Heinrich Hertz, who the unit Hertz is named after, up there in the corner for you again. And it turns out that because these two are inverses of one another, we have a couple other relationships that I've tossed up here on the screen. You really should jot one of them down. You don't necessarily need both because you're skilled enough at algebra that you can flip-flop them, but certainly you're welcome to. And all of the period formulas have the same seconds measurement, and all of the frequency formulas have the same hertz units. There are two basic types of waves. You've seen these a couple times before, but first off is a longitudinal or compression wave, where the disturbance and the propagation, that is the shaking and the direction that the wave moves, are in the same direction. And an example of this is sound and primary earthquake waves. There's a quick sketch of it. You don't need to worry about the terms on there, though, because we'll label parts of a wave on the next slide. So the other type of wave is a transverse wave, and here the disturbance is up and down while the wave motion is still side to side, or at least that they're at right angles to one another. It could be that the disturbance is side to side and the motion is up and down, but the two are at right angles to one another, whereas with the longitudinal or compression waves, are parallel to one another. Examples of this include light and secondary earthquakes and water waves way out in the ocean again, and here this is kind of your stereotypical wave that you probably think of. It's a sine curve. Anyway, parts of a wave. You want to sketch these diagrams. So the top one has some squished parts and then some not so squished parts, not so squished parts. The bottom one's kind of your classical wave. So some parts of the wave. First off, direction of travel. Both of these are traveling horizontally. Keep in mind we, of course, could rotate these images, but direction of travel compared to motion of the disturbance. And so for the top one, the compression wave, it's side to side, where matching the direction of travel, whereas for the bottom one, they are perpendicular to one another, the direction of travel and the direction of the disturbance. Compression is the squished in area here, or at the beginning and end, and it's related to the crest or peak of the bottom wave, and that's compared to refraction. Apparently I labeled refraction next. Or refraction is the unsquished part, and trough that's equivalent to the trough or the valley of another wave. Here's wavelength now. Wavelength is the distance from one part of a wave to the matching part. So for a compression wave, it's from compression to compression. You could do it from refraction to refraction. For a transverse wave, it's from midpoint to matching midpoint, or from crest to crest, from trough to trough, or from any point to its matching point later on. And lastly, the height from the center line is called the amplitude. And it is the height measured from the center. It's not the whole height. Anyway, since speed is distance divided by time, but for waves we measure distance with something called wavelength. It's abbreviated with this upside down y, which is the Greek letter lowercase l lambda. And since time is measured as period in seconds, we can get the wave speed formula is equal to wavelength divided by period. It's the same as the speed formula that you've had before, but now we have just different terms in there. Instead of speed, it's wave speed. Instead of distance, we call it wavelength. And instead of period, instead of time, we call it period. And abbreviated, that's v equals lambda over tv for velocity, of course, here, instead of speed. I don't know why we call it wave speed, but then use velocity in the abbreviation. I suppose direction maybe does matter, but anyway, we also know that since the period is equal to 1 over frequency, that we could substitute frequency in for the period, and we end up with another formula that wave speed is equal to wavelength times frequency, or v equals lambda times f. Of course, both of these are speeds, and speeds are always measured in meters per second. Interference is when two waves interact with one another, and I always think of interference as a bad thing myself, but for physics you can have constructive, which is good, or at least building up interference, and destructive, which is bad or destroying interference. And so there are two types of interference: constructive, where waves build up to increase amplitude, and destructive, where waves cancel to decrease amplitude, and it turns out they can negate each other totally. I'll do a diagram of that in class at some point. I don't have an image on this slide to go with this one, so just remind me and I'll do that diagram. As a side note, the waves are still remembered as they interfere with one another. So you have two waves that are going past one another. They interfere while they're going past one another, but they don't interfere permanently. They end up separating out later on. If the conditions are just right, you can get something called a standing wave, and a standing wave forms when the rate of reflection, that is, waves can reflect and bounce back into their original medium, it matches the rate of incidence, or the incoming waves. And so the rate of waves coming in matches the rate of waves coming back out, and you can end up with a wave that appears to stay stationary. And this creates things called nodes, which are the stationary points along the midline, as well as antinodes, or crest and troughs. But you end up with a wave that appears to be staying still, but the energy is still going back and forth. Really, it's just interfering with itself in a perfect way. But that's a standing wave. The Doppler effect is an apparent change in wavelength or frequency due to a moving source. And we'll talk about the Doppler effect both with sound and light. And there's a photo of Christian Doppler up there. But it's a shift in the wavelength that causes an apparent change in frequency. Because the source that's emitting the wave is moving proportional to the wave itself. When the source is moving fast enough, then you can actually get bow and shock waves from the source that's emitting the wave itself. And so if the source is moving fast enough, you end up with a bow wave. It's named after the front end of a ship, where these were originally noticed in water. And if it's three-dimensional, we call it a shock wave instead. And here's just an awesome photo of you can actually see the 3D sphere of a cloud forming here on the back of a Blue Angel F-18 jet that's traveling faster than the speed of sound, and so you can actually see the shock wave here, and a spherical, or at least a front edge of a sphere cloud forming right at the it'd be right behind the compression, and then you can also see the ripple track that it's leaving in the water behind it. And we'll do more with bow and shock waves when we actually get to individual special types of waves like sound and light. If you have any questions, be sure to jot them down and bring them with you to class.